What's up, guys? Today we're going to be doing combination sum. Combination sum is currently being asked by Amazon, Facebook, Google, Microsoft, Airbnb, and LinkedIn, so a whole lot of companies. So let's get into it. What's up, guys? So like I was saying before, today we're doing combination sum. So the problem description says, given a set of candidate numbers and a target number, find all unique combinations in candidates where the candidate numbers sum to target. The same repeated number may be chosen from candidates an unlimited number of times. Then it says, note, all numbers including target will be positive integers, and the solution set must not contain duplicate combinations. So cool. Just to make sure we understand the problem, I wrote the description ahead of time because this is a pretty long one. The description is, our objective is that we need to find all unique combinations summing to target. We have two arguments. We have candidates, which is a list of integers, which could represent the possible numbers that go in our path up to a target. And then we have target, which is an integer, which is what we're trying to sum the things in our path to. And then we have ret, which is just, like I'm calling our return value ret, and that's just a list of lists where each sublist adds up to target. So looking at the notes and what's right above the note, we get a good error checking case right away. So essentially, if we don't have any candidates, or in the other case, because all values have to be positive, if our min candidate is greater than target, we can just return an empty list. Otherwise, we're going to initialize this ret list, and we're going to return it after we do a lot of work. So this is where we do the work. So let's just talk about this problem for a sec. So it tasks us with finding all unique combinations. Anytime you hear the term find all or like find an exhaustive list, that kind of tells us that it's a backtracking problem. And backtracking is something that comes up in a lot of computer science and is super important, but it's always been like kind of magical. But I'm going to try to talk to you guys about how I think of backtracking. So essentially, when I think of backtracking, I think of state, I think of decisions, and then I think of base cases or termination conditions. So essentially, we're going to need to be keeping track of state. There's three things we want to keep track of: our candidates array, we want to keep track of the index we're currently on. So essentially, we're going to either go forward another index or stay on that index. And that's going to go into a decision because that's a choice. And then we want to see our target. So if we're decrementing our target down to 0 by adding 2, 2, and 3, what's our target currently at? Because we first subtract 2, then it becomes 5. We subtract 2 again, then it becomes 3, and then we subtract 3, and then we get 0. So we want to keep track of that as well. So now we have our decisions. So this is each time we're going to call the function again. So our decisions are, we want to pick one. So either we pick that number and then we move forward. We want to pick one and then pick it again. So we pick that number, move forward, or pick that number, add it to our path, but then don't move forward because it says we can use numbers multiple times. And if you look at example 1, they use 2 twice. And then the other one is that we could skip the number. So essentially the way that these decisions would change state, if we pick one, we want to increment our index 1. We want to decrement our target minus the value at our index. And then we want to add what we currently picked to our path. So I guess we could consider path as part of our state. So we'd add candidates at our current index. And then the ways we change these for picking one and then picking it again is, if we wanted to pick it again, we wouldn't move forward an index. We just decrement it from target and then add it to path. And then if we want to skip one, we would just move forward. We wouldn't decrement target or change path. So now we have our base cases, our termination conditions, and essentially we only have two cases. Either it's a valid path, so if target equals 0 because we've decremented down to 0, and also the path is not already in our ret array, then we just append path to ret, And then our other case would be if target is less than 0, we just want to backtrack. So this kind of comes into like where the magic is of what actually backtracking is. So essentially, in a question like this, in a backtracking problem, each decision we make is going to be a call to the function. So essentially, call function changing state. So for each one of these decisions, we're going to call the function, the helper function, and then change the state in this possible way. So because it's just a depth first search, a way that I like to think of it is like you're walking through a maze, and each time you take a step, that's a decision. So that's a call back to our function that we've taken a step, and then what that does is essentially it makes a new function call on the call stack where we can do things. If we get to the end of the maze and there's nowhere we can go and we haven't reached our destination, essentially all we're going to do is we're going to terminate on that call to the function in the function stack. So you can understand that more, I'm probably going to play some code visualizer or some Python tutor visualization of making a decision, adding a call to the call stack, and that'll be on my left or my right. What's up, guys? This is future me talking about backtracking with the solution that we just coded up with all the state, decisions, and base cases that we just delineated above. So what this is doing is, like I was saying earlier, backtracking is just making a call to our function at each decision it wants to make. So when we make a call to this function, it's going to make a new call on the call stack, and in this case, our decision was likely a pick one decision because we decremented from our target and incremented our index. So now that we have a new call on our call stack, we want to see if this meets any of our base cases or termination conditions. And in this case, it does. The target less than 0, which tells us that we want to backtrack out of this call to the call stack because we know that this isn't a solution that we want. So our return value is going to be none, and then we're going to return out of this function because we don't want to add it as a solution. So essentially, all backtracking is, we say backtrack on line 21, we're just returning, and then this is backtracking. So cool. If that makes sense, let's implement this. So essentially all the work we're going to be doing is just in some recursive helper function. And like I was saying, since backtracking is just using a DFS with certain choices, I'm going to call this helper function DFS. And then we want to pass in all of our like possible state. So we want to pass in candidates. We want to pass in the current index we're at. So I'll call this 0. We want to pass in our target. We want to pass in our path, which is just going to be an empty array at this point. And we want to pass in ret. So let's make sure we're not missing out on anything. Yeah, it looks pretty good. So now, given that we can implement this DFS correctly with the state, decisions, and base cases above, this should work. So we have DFS, going to have self, candidates, index, target, path, and ret. And then for the sake of simplicity, I'm going to change candidates to nums. So then first I want to implement our base cases. So if target equals 0 and path is not, if path not in ret, I just want to append this to ret and then return. And this is essentially the backtracking because we're ending this call in the function. If target is less than 0, we know that this isn't a path we want to take, we want to return. And then this is our other backtracking step. So then now all we want to do is just make these decisions. So like I was saying above, it's just pick one, and then pick one will just be a call to self.dfs. And what we're going to be changing, we're going to be passing in nums just the same. We want to be moving our index 1 forward. Oh man, let's do this quickly. We want to be decrementing our target minus the value at nums. And then we want to be adding this to our path plus nums at index, and then we want to keep our ret array. So now we can use these to do the other ones. So to pick one again, we're going to be doing all the same choices, but we're not going to be altering our index. And then just to skip one, we're going to be altering our index, but not decrementing our target or adding to our path. So essentially, if there's not any errors, this should work. Let's run this example first. Okay, list index out of range. So we actually forgot one case on line 43. It's the case that index is greater than or equal to the length of our nums, because we don't want an index out of bounds exception. Cool, so this looks like it works. Let's run it. Awesome. So there is an optimization that could be made. Essentially what we could do is we could just have a for loop, and we could say like for I in range index to len nums, and essentially all we're doing here is we're just going to call this self.dfs of nums target minus nums at I, and then we're going to be passing in I because this will skip it or pick it, and then passing in path plus nums at I and our ret. But essentially, I like to use this pick one again, and then skip one, because I think this really clearly shows all the choices being made. And cool, that works. So I hope that made sense to you guys. If you like it, please leave a like and comment if you want me to do any other different problems. Thanks so much for watching. If you like the videos, subscribe to my Patreon, and I'll see you guys next time. Peace.